star of E of something is what? A alpha times. Okay? So this is alpha times mu star of E is a Lebesgue measurement set. So by the definition, this is alpha times mu star of T inverse. But when you take T of E, mu star is alpha times mu of this. When you take T inverse, it will be 1 by alpha times. So this is equal to alpha into 1 by alpha into mu star, which is mu star. This means if E is Lebesgue measurable, TE is also Lebesgue measurable. And because T inverse is a map of the same kind, converse is also done. So E is Lebesgue measurable if only is that is true. And of course, you know that mu star of T of E is alpha times. In particular, if I take alpha equal to 1, then mu star of T of E equals mu star of E. And what is then T? T of x equals x plus beta. This is nothing but a translation of the origin. So if you say Lebesgue measure is translation in variance. Wherever you move the origin, the Lebesgue measure will not change. Now all this will go through in Rn. How do you define the Lebesgue measure in Rn? You go through the same process. Now your P will be product I equals 1 to n of Ai Bn. Boxes. Now you go through mu star. Define the outer measure in the same way, and then define Lebesgue measures, Lebesgue measures in the same way. Everything you can do, all that I have done now, you just go through. So in one stroke, in all dimensions, you can define the Lebesgue measure, and all of them are translation in variance. Now in the one-dimensional case, we have this alpha. In the n-dimensional case, an affine linear map is of the following form. I took A equals identity for the translation. Otherwise, this is called the affine linear map. Then we can show that the measure of T of E is equal to the measure of E multiplied by a number. In one dimension it was alpha, here it is modulus of the determinant of E. So the determinant of a matrix, when you apply a matrix in Rn, you are making a transformation. So if you have a set, it will get deformed. Now the volume of the set, new set, is modulus of the determinant of the A of A times the volume of the whole set. So that is the meaning of determinant of a matrix in geometrical terms. It is how the volume changes when you make a transformation. Okay, so that is how determinant can be viewed geometrically. So if you take the unit ball, it will deform into some set, The volume of the unit ball will be modulus determinant K. If you take the unit cube, it will be formed into a parallelepiped. The volume of that parallelepiped will be modulus of determinant A times the original volume. So that is the meaning of determinant of a matrix from a geometrical analysis point of view. Okay? It is how volumes change when you make a transformation. Okay. So what are the important properties of the Lebesgue machine? Which you should know. For all compact sets K, mu of K is finite. The measure of every compact set will be finite. If E is Lebesgue measurable, mu of E is the infimum of mu of V. E contained in V, mu. So essentially, if you know the value of the measure of open sets, then you know it for all Lebesgue measurable sets. Because every Lebesgue measurable set can be approximated from about by open sets, and the measure is given this way. So entirely the open sets will dictate, and open sets are the model sigma. Mu is translation in the range. So if you shift the origin, nothing will change. In fact, in Rn, if you have an orthogonal matrix, what is the determinant? What is the determinant? If you have an orthogonal matrix, determinant is plus or minus 1, so modulus is 1. Okay? So if you have an orthogonal matrix, the measure will not change. But what is the meaning of orthogonal matrix? It's either a rotation or a reflection. So if you have translation, rotation, reflection, all these are rigid motions of the body, then the volume will not change. This is intuitively obvious. Lebesgue machine has that. So if you have these three properties, then modulus defines the Lebesgue machine itself. So Lebesgue machine is a unique measure up to a constant multiple of which has all these properties. So let us take the example of the matrix. It's a very good set for counter examples. So you take x equals 0, 1. And you define x1 to be 1 by 3 to be. Means the middle 1/3. Define x2 be 1 by 9, 2 by 9, union 7 by 9, 8 by 9. So x2 will be this interval, union this interval. And now you know how to go on defining various x's. x3 will have 4, which will be the middle thirds here, and so on. And now you take x minus union x. That means I have rubbed this off, I will rub this off, I will rub this off. They sell it fully, more or less, there's nothing left. Okay? So each xn is a union of open intervals, so it is open. Union of open sets is open, therefore C is closed. What is measure of x1? 1 by 3, length of the interval. I won't put star anymore, okay, because I defined level measure. Therefore, I remove that star, I don't need it. Mu of x2 is 2 into 1 by 3 square. Mu of x3 is 4 into 1 by 3 cube, and so on. Okay? So in general, mu of xn equals 2 power n minus 1 by 3 power n. And all these are disjoint sets. Okay? So mu of union xn is sigma 2 power n minus 1 by 3 power n equal to 1 to infinity. This is a nice geometric series which you can easily sum. It's 1 by 3 into sigma 2 power n minus 1 by 3 power n 1. And this is so what is mu of C? Zeros. Because mu of the original interval is 1. In that I remove union xn which I also measured 1. So mu of C is 0. Any x is 0, 1. I can then write it as a ternary expansion. So 0 point x1, x2, x3, etc. Where xi is 0, 1 out. Okay? This is nothing but sigma xi into 1 by 3 power n. This is called the ternary expansion, like binary expansion, ternary expansion. The expansion in terms of 10 is the usual decimal expansion. So this is just 1 by 3 is instead of 1 by 10 or 1 by 2, I am using 1 by 3. This is the ternary expansion. So this is 1 by 3 power x. Sigma xi into 1 by 3 power I will give you the ternary. How do you define this xi? So each first time to define x1, I divide into 3 equal parts. If it is here, it is 0. If it is here, it is 1. If it is here, x1 will be 2. Then to define the next component, I divide each of these into 3 parts. If it's in the first one, I will put 0. The second one, I should put 1. If it's in the third one, I should put 2. You don't get it. So I want to write it as sigma xi 1 by 3 power. So I will only tell you what's happening. You go home and think for yourself. Now x1, for all numbers here, x1 will be 0. Here x1 will be 1. Here x1 will be 2. Now you divide this into 3 parts. Here x2 will be 0, x2 will be 1, x2 will be 2. Here x2 will be 0, x2 will be 1, x2 will be 2. Here x2 will be 0, x2 will be 1, x2. Now you divide each of them into 3 equal parts. Then in the first one x3 will be 1 and 0, or 0, 1 and 2, 0, 1 and 2 like this. Now what have I done here? I have removed the middle third every time. That means I can set the set of all x such that xi is equal to 0 or 2 for all. 1 will never because the middle interval every time I am removing. So in the ternary expansion I will have only 0 or 2. This implies that C is uncountable. Use the usual Cantor diagonalization argument. Suppose I know I can order them in some way. So the first number will be x11, x21, x31 and so on. The second number will have 0.x21, x22, x32 and so on. The third number will have x31, x32, x33 and so on and so on. So I can number all the numbers I assume I have listed. And all these xi's are going to be only 0 or 2. Now I create a new number. I look at the first element of the first number. If it is 0, I will put 2 here. If it is 2, I will put 0 here. Then I look at the second decimal of the second number. If it is 0, I will put 2 in the decimal, second place. If it is 2, I will put 0 here. Like this I go on doing. Then this new number is not in this list. Because for every number here, it is differing in some decimal place. This is the usual Cantor diagonalization. How do you show real numbers are uncountable in the same way? Okay? So, if you list all the elements in the Cantor set, I can produce a new one which is not in that, which is still in the Cantor set. So Cantor set has to be uncountable. Okay. So Cantor set is an example. You know that every countable set has measure 0. So Cantor set is an example of an uncountable set which is of measure 0. And it is the source of all kinds of counterexamples. For instance, there is a property that if mu of E is 0, if mu star of E, the outer measure is 0, then E is Lebesgue measurable. Every set with outer measure 0 is Lebesgue measurable. And if F is contained in E, F is also Lebesgue measurable. The property which says that Lebesgue measurable sets are complete. So if you take any set of measure 0, it is measurable and all subsets of it are also measurable. Okay? Now Cantor set is a set of measure 0. So every subset of the Cantor set is Lebesgue measurable. So how many sets are there? What is the cardinality of the power set of the uncountable set? It is called 2 power c. This is the next higher cardinal. Okay? So, number of Lebesgue measurable sets is at least 2 power c. And in fact, it is equal to 2 power c because anyway, cardinality of the real line is also c. Okay? And one can show that the Borel measurable sets have a cardinality at more c. So there exist Lebesgue measurable sets which are not Borel measurable. I told you that the sigma zebra was a strict inclusion. This is one proof. In fact, but using the Cantor set, you can construct something called the Cantor function, which will give you another beautiful set of counterexamples, and you will explicitly construct a Lebesgue measurable set which is not Borel measurable. Now we will look at measurable functions. Okay. So you take x S is a measurable space. This means X is a set and S is a sigma value. And F is from X to real value function. But R union can also, let's say, take these values. We say that F is measurable. So a set being measurable means it belongs to the sigma. A function being measurable means it obeys the following definition. For every alpha in R, set of all x, f of x bigger than alpha. Now you take set for x, the fx is less than or equal to R. So this is nothing but set for x is fx bigger than alpha complement. So if this is in S, the complement must be in S. So this implies for all alpha set for x fx less than or equal to alpha. So let us take set of all x and fx is strictly less than alpha. This is equal to intersection n equals 1 to infinity. Set for x fx is less than or equal to alpha plus 1. It's less than alpha plus 1 by n for all n, then it is strictly less. Sorry, alpha minus 1. Union. Very good. Okay? This is correct? Therefore, but we know that each one of this is in S, countable unions are in S, so this implies for every alpha, set of all x is fx less than alpha is in S. But if some set is in S, its complement is also in S, therefore this implies for every alpha, set of all x fx is greater than equal to alpha is in S. So, set of all x, so set fx is strictly bigger than alpha. Is again union set of all x. Fx is very big for alpha. So all these are in S. Place this also in S. So this is the same as saying F is measurement. So for the definition of measurability, strictly bigger, no? Plus one. Okay. So, for the definition of measurability, you can use many of these conditions. They are all equal. E3 place here. We have completed the cycle. So, all of these are definitions of measurability. Then of course you can prove all the usual theorems. Sum of measurable functions is measurable, product of measurable functions is measurable, and so on. Okay. Analysis. That means we are going to take limits, convergence, and so on. So now, before I proceed, I want to make one remark. If μx is finite, in every set has finite measure, we said mu is a finite measure. A particular example is suppose μx equal to 1. Okay? Then you call it a probability space. Because probability theory is essentially what we are doing is measure theory. X is the set of all, is what is called the sample space. The sigma algebra is nothing but the collection of events. Mu, the measure, is nothing but the probability. Probability of the entire thing happening is 1. So if you go back and look at the axioms of probability, you will find it's precisely the axioms of measure theory which we have been looking at. The only difference between probability and measure theory doesn't deal with what probability has, is the notion of independence. Okay, that is one notion which we don't have. What is a random variable? It is nothing but a measurable function. So this is how you connect results between probability theory and measure theory. So what we are going to do, in some sense, applies many things to probability. Only thing is, independence of random variables is one notion. We don't have that notion in measure. That is an extra special notion for probability. Otherwise, a random variable is nothing but a measurable function. A probability is nothing but a measure of finite measure on some sigma algebra of some sort. That's all. So that is how probability theory works. Okay. So now you have Fn, sequence of measurable functions. So what are the notions of convergence? So let's say F is also measurable. So Fn of x converges to f of x for all this. This means point place as usual. The second notion is Fn of x converges to fx. This is the notion which is most common in measure theory. For all x in x except possibly on a set of measures here. So it converges at all points, but the convergence may fail for some points on it, but that set of points is what is called a negligible set or set of measure 0. This we say that Fn converges to F almost everywhere. AE means almost. There is a third notion of convergence. This This is weaker than this. Okay? So it's called convergence in measure. So let me define that. So we say that Fn converges to F in measure notation from this is Fn goes to F if for every epsilon possible there exists an n such that for all n greater than equal to n, the measure of the set for all x is that mod fnx minus fx greater than equal to in some way we are measuring how non-convergent x sequence is. The set where it violates the notion of convergence, then the fnx minus fx bigger equal to epsilon, that must be a small set. Or equivalently, limit n tending to infinity mu of alpha x is fn minus fx. Beginning to epsilon. Which one? This is stronger. This means it converges at all points. In fact, if you have convergence in measure, it may not even converge at any point. I'll give you an example now. Okay? But if you have a set of finite measure, then it will see all this. So convergence in measure is a weaker notion of convergence. Okay, it says, okay, it doesn't converge, but where it is far away from the limit is a very small set. That's all it says. Okay, so we will see example and one or two properties of this, and then go on to define integration. Okay, so that we do that.
Today we will see what is suitable examples Um, so, what is the motivation for defining the topological space? We all know notion of metric space. Okay, I'm sure you must have studied already. You must have even taught analysis where the notion of metric space plays a crucial role. You have a notion of a metric, and then given a metric, you have these open balls, and then you say a set is open if it can be expressed as a union of open balls. Alright, and then you have a notion of a closed set, and so on, limit point, and so on. Okay, these notions you want to have in a situation where there is no metric. So without the notion of a metric, how do you define closeness? Okay, neighborhood, notion of a neighborhood. When you say two things are close to each other, these concepts are captured by just giving yourself a collection of sets which you will call a collection of open sets. Okay, and they will satisfy the expected properties. By expected properties, what do I mean? Properties which are true or valid in the context of metric spaces. Okay, so I am going to write down, just for the sake of completeness, the axioms for a topology, and then we will see how various notions that are familiar in the context of metric spaces are generalized to the context of topological space. But one thing I should say, I mean, more than just lecturing here, giving definitions and examples and so on, when you teach topology, always remember that a picture is worth 1,000 words. Draw pictures. The way you draw pictures not only should bring out the concept you are studying, it will also guide you towards the proof. Okay? So, how to draw pictures? If you look at Mankare's book, almost every page there will be some picture or the other. But when you teach in a formal classroom, quite often that is forgotten. You just state theorem and then definition and then just start proving things in a formal way. Of course, when you write a proof, it has to be written in the most formal way. But always draw diagrams which will aid in understanding. Okay. Just make small plans on the lecture, you will take out the notes. Okay. So, what is a topological space? So, you start with a set. A set X together with a correction of subsets of X is called a topological space if this collection, so like X round bracket tau is a topological space if tau satisfies the following conditions. So I write here the empty set and the whole set are members of this collection. So members of tau will be called open sets. Okay. Number 2. So tau is closed under arbitrary union. That is, what does that mean? So U alpha in tau alpha in J implies union over Q alpha alpha in J is also another 3 term is closed under finite intersection. Finite intersection. So that is, so you write, suppose U1 and U2 are intersect, then so is the intersection U1 intersected UN. Okay. Notice that if X is a metric space and this is a collection of all open sets in that metric, with respect to that metric, then of course empty set and the whole space are always open, and U alpha in J, some indexing set, is open for each alpha, means the union of U alpha is also an open set in the metric space, and finite intersection of open sets is open, okay, in the metric space. So this is the character. These axioms sort of hold in the context of metric open sets of metric spaces, and this is what leads to the notion of a topological space. Okay. So members of O are called focuses. So immediately we see some examples. Alright. So this lecture will be mostly full of definitions, examples. Maybe in the case of some examples, some proofs will be given, but proofs of many theorems for want of time will be given. So first example is that of real numbers. What is open sets are empty set, okay, empty set, space, okay, intervals, and so open intervals, A comma B, and then